Okay. So the title of my work the last few weeks was a computational look at the energy splitting in titanium ions and octahedral and tetrahedral coordinations. And so when we take a look at molecular orbital theory, we see that the d orbitals of these transition metals are going to be split with the tetrahedral on the left and the octahedral on the right. Um, and these symmetry labels are determined from the molecular orbital theory. And so I kind of wanted to take a look at how these split and trying to determine some of the energies that correlate with that. So when we look at an octahedral, um, another kind of splitting can occur after the original field splitting, and that's called the Jahn-Teller effect. And so what this does is it tries to optimize the total energy of the molecule by rearranging orbitals so that the spin is in the lowest possible conformation. And this can be done in two different ways. Um, okay. Um, well, it can be done, there's another side that can be done in two different ways, both by elongation and by compression. And so uh, with the elongation, it's similar to what we see on the screen here, where the z orbitals are going to be lower in energy, but as compression occurs, the orbitals with the z component are actually increased in energy because elongation and compression are done along the z vector. Um, and so what we have here is the hexaaqua molecule, and I have listed the HOMO through the LUMO +4. This is a D1 electron configuration, so we expect to see the HOMO in the first of the D characteristic orbitals, which is shown here. And the following corresponding d orbitals are also shown. F is shown just to show that we lose the d character, and we go back to a p state in the f orbital. The energies we can see here, they're actually grouped relatively similar, with the lower energies being the first three and two higher energies, and that shows good correlation to the octahedral splitting. The difference in the first three can be somewhat correlated to the Jahn-Teller effect, even though with only one electron, it's actually a very weak effect. For this one, with the hydroxyls on it, we show in the first one that the HOMO should be the last of the p states because this is a d0 electron count, which it is for the HOMO. And then for the LUMO through the LUMO +4 are all d state, or have d characteristic orbitals, which is what we were looking for. When we also look at these energies, we can see the first two of the d character have a lower energy than the top three, and I'm not exactly sure why these would be splitting, as there are no d orbitals, so I don't know how much of a Jahn-Teller effect actually occurs. And so all of these charts are sideways, but these are the density of state spectra that are produced with the spin-polarized method of the optimized geometry after heating of the molecule and after running molecular dynamics within the VASP software. And so I guess I'll just try and play a few movies in the last couple minutes that I have here. This one is just the VASP heating of the hexaaqua molecule. Pretty awesome, I know. We'll go to the next one. This was the molecular dynamics. They seem to be very similar in what they're doing. Another important thing we did was we ran TD-DFT on these, and after we got the absorption spectra, we see the absorption. This one was the peak was near 571 in the visible range. Literature has it anywhere mid 490s to 520 is what I've seen. So there is some discrepancy with the actual absorption peak, but this absorption matches what we see in the lab, where this is a titanium 3 chloride solution, and so with the absorption in this 5 to 600 region, um, essentially we should be seeing the red and the blue and the purple emitted, so this matches what we've been seeing. But the rest is for the tetrahedral geometry, and because this is a D0, we should expect to see. We don't need a spin polarized method, and so that was seen, and these are the density of states. I also have a couple movies of the heating and the molecular dynamics, but with what I have left, I want to show this was the hexa aqua titanium, but this was in a number of water molecules, and so we were taking a look at how it actually interacts with water, just not by the ion itself. And so this is a rather short video, but that's what we found. So we found that there was reasonable evidence for the splitting that has been shown through other theoretical methods. And so I was pretty happy with the way it turned out. So thank you.